Okay, everyone, please welcome Harald Welte to be talking about open source mobile communications.
Yeah, hi everyone. That was quite an adventurous beginning of the talk. Never happened before. Okay, so I'm going to talk about open source mobile communications and particularly the Osmocom project, which some of you may have heard about before in various different contexts. And before I'm going to talk about the various sub-projects and the various focus areas in which we work inside the Osmocom project, I'd like to take a little bit of a step back and compare different communication worlds or different communication systems, sort of to reflect the journey that we've gone through the last 8 years by now. So going to skip the slide about myself. Basically, I've been doing Linux and networking related stuff for quite some time. And if you have a background in TCP/IP, the internet world, Ethernet, Wi-Fi, whatever, then it's basically to you it's normal that all the stuff you want to use is open source, or at least you can find everything in open source. So basically, let's say you want to do some research in the TCP/IP world. Well, you use off-the-shelf hardware like an x86 PC, which has an Ethernet card built in these days. You start with Linux or BSD operating system, which has the entire protocol stack and the drivers and everything open source. You add whatever instrumentation you need. You do some modifications. Let's say you have a bright idea how to optimize TCP congestion control or something like that. You do testing and you write a paper and publish the results. And this is why we have been seeing such an enormous amount of innovation in the TCP/IP and internet world over the last 25 years or so, and we haven't seen that in the cellular space to the same extent. So assume it's 2009, which is basically before we really got started in the Osmocom project, and you want to do some research into mobile communication systems. Where at that point, until 2008, there was no implementation of any of the protocols or functional entities in as free and open source software. And even, let's say, if you do this in an academic context, you would find it quite hard to find universities that have a test lab with all the required equipment. So I'm in Germany. I know 2 universities that had a full GSM network in there at the university. But even if they do, well, then all the equipment is black boxes. So you can basically say, okay, well, this is the black box that implements the MSC, and there is another black box that implements something else. And then you can do some protocol sniffing on the interfaces between those black boxes, but still, it's not really all that exciting because you can't modify those black boxes. And the only chance you had at that time to do some research into cellular systems, mobile communications, is to partner with one of the large companies that build this equipment, let's say Ericsson, Huawei, ZTE, Nokia, Siemens Networks, and so on. And then they put you under an NDA and will profit from your research, and you still, well, yeah, maybe you can do some interesting research, but you can't really publish all the results and so on. So, and if we compare these 2 sides, basically the internet side with TCP/IP, the Ethernet, Wi-Fi, and so on, all those protocols, and we look on the other hand side at the cellular world where like GSM, GPRS, Edge, 3G, HSPA, LTE, all those different systems and generations out there, you will find that the specifications of both of those worlds are always open and publicly available. So if you want to learn about TCP/IP, you can read the RFCs. If you want to learn about Ethernet, you can read the IEEE specs. If you want to learn about GSM, you can go to the ETSI or to the 3GPP websites where you can find a comprehensive body of standards and specifications, and you can learn about them. So the documentation for both of those worlds, or for systems and protocols in both of those worlds, has been public for a long time. But yet, if you look on the internet side, you have all this innovation and all kinds of people doing interesting research. and also going beyond just like research into functionality, going into security, for example. All the journey that the internet world has had, you know, from ping of death to DOS attacks to all those and much more comprehensive attacks these days. All that has not happened until a couple of years ago, and is still not happening to that extent in the cellular sphere. And the reasons I find for this is because, well, the industry in the cellular world is extremely closed, and I have to add closed-minded in many cases. And you find very few protocol stack implementations, proprietary, of course, all of them. And the chipset makers, talking about the handset side now, are not releasing any documentation on the hardware. So even if you say, well, okay, I move away all this proprietary protocol stack, I'm not interested in it, I want to write my own, you don't get the documentation that's needed to understand the hardware to the extent that you can actually implement your own protocol stack on top of it. So the only choice you have is to do reverse engineering, which means you spend an awful amount of time doing things which are not those things that you really wanted to do, which is implementing a protocol stack, or even doing security research or any kind of research. So now some people think about, oh yeah, all this research, and in particular from a security point of view in telephony, who is interested in listening to phone calls? I mean, we all know the government can do it anyway. We all know there is lawful interception interfaces in all the cellular equipment out there that's documented and specified, and there are laws around it, and so on and so on. But I think listening to phone calls is boring indeed, but there's much more interesting stuff out there. We have machine-to-machine communication. We know that BMW cars can be unlocked and locked using GSM. It's not only BMW can do that, unfortunately also other people can do it because they were not very smart when implementing that. I'm not talking about the brand smart here. There is alarm systems that often burglar alarm systems that can be that either report over GSM or can be unlocked. There's of course smart metering. There is one topic that I still haven't seen a lot of research in, which I think is a very interesting area, is railway GSM, GSMR. Not sure how many people in this room realize that railways and basically permission to enter certain tracks and the speed permit to run on certain tracks is communicated by GSM, at least in some tracks in some countries in the European Union, and more of those tracks get converted to railway GSM. We have vending machines that report if the cash box is full. So if you want to be smart and a thief, then you could use, for example, such messages to know where there is lots of coins in the cash boxes. There is entire wind power plants, windmills that are controlled over GSM in the end, so whether they feed into the grid or not. Just think about what it does to the grid once people can look at, or not look, but rather control such interfaces. We have transaction numbers for electronic banking that can transmit it over SMS, and banks sell that as a secure method of authenticating. I mean, not sure what they had smoked when they make such a statement. It's to me it's ridiculous. Anyway, so there's all kinds of interesting things from security point of view, from just the technology point of view in the cellular world, and there hasn't been much free software. So we started what's called the Osmocom project, open source mobile communications, with a typo in the name. That's of course just my slide and my inability to read the slides before presenting them. And it's a classic collaborative, community-driven free software project. So there's not a single company behind it. There is no dual licensing. There is no open core. There is nothing. It's mailing lists and people and code, and everything of it is released. And Osmocom gathers a number of people who explore this world of that's very industry dominated and very closed in terms of implementations and often also technology. You can check out, of course, the website. Yeah, we also have sour code. No, it's source code in Git. We have lots of information in a wiki. And yeah, you can check it out. And there's many different projects inside the Osmocom project. So Osmocom is the umbrella project, and within Osmocom we have many different projects. I don't even know the figure right now, but I would say it's probably 24 or so active projects at this point. So it's a little bit, I mean, of course not in scale, but you think of like the Apache project. Well, yes, there is an Apache web server, but there's thousands of other projects that they do under the umbrella, and it's a similar situation with Osmocom on a much smaller scale, of course. So the first project that was publicized about and that was released is called OpenBSC, and it implements what's called an ABIS interface towards what's called a BTS, a base transceiver station. So basically using OpenBSC and a base transceiver station for GSM, you can run your own cellular network. And that's, I'm going to talk about in a workshop later at EMF Camp. If you're interested in that, feel free to check out that workshop. We're going to run through installing the software, configuring it, setting up the device, and actually getting to the point where you can run your own cellular network with OpenBSC. It has various different modes in which it can operate, but that goes into a lot of details on all the different acronyms and functional splits in the GSM architecture. It's deployed, well, it's more than 200 now. I'm sure it's more than 500 confirmed installations that I know by now. But of course, well, it's a free software project. Anyone can download it, anyone can run it. I don't need to know about that. So there can be a much higher figure that we knew. So as we are at a camp, actually this is a reminder to another camp that happened a couple of years ago, the Hacking at Random Camp 2009. And the picture that you can see is at the bottom of the tree, there is two 48 kilogram Siemens base transceiver stations, a couple of cables running up the tree, and you see the red tape, well, not figuratively, the literal red tape around the antenna, taping the sector antennas to the tree. And that was the first test installation that we ever did with the OpenBSC software. So at the Hacking at Random Camp in 2009, we were running a cellular network for participants of the camp, but also for us to basically have a real-world test for our implementation of those protocols. This has become sort of a tradition. So at other events in the Netherlands or in Germany at the CCC camps, also at the congresses, we have been coming back every so often and rerun this network, always with new features, new equipment, and so on. So it can be used in several different modes. Not going to go into too much detail here. Basically, one of the two modes enables you to run your base stations as part of an existing cellular network. Well, if you're not a cellular operator, it's not a very interesting mode to you, because, well, if you don't happen to have an existing cellular network, how do you integrate with it? And the other mode, which is much more commonly used in the community, is what we call the NITB, the network in the box. And that's basically, well, the name, as the name implies, all the elements that you need for a GSM network are implemented in one box. So you don't need all this complicated setup of, a half a dozen of different components and configure all the interfaces and so on. So it's just one program, you start it, and you attach your transceiver hardware, and that's it. So that's very suitable for private and or autonomous small networks, like a PBX, but with a wireless interface for the actual phone. There is no dependency on external components, so you don't need anything else but this OpenBSC and the transceiver hardware. You can, if you want to, connect to the outside world using ISDN or VoIP or whatever you feel fit. Basically, we have an interface how we call them MNCC handler, mobile network call control handlers, can register. You can interface that with asterisk, with FreeSwitch, with whatever you want. There are some people who run this, for example, on offshore drilling rigs for oil and underground mining as an alternative to PMR, professional mobile radio. Because, well, professional mobile radio has professional in the name, which means all the equipment is like 10 times more expensive. So if you can use inexpensive phones and GSM phones you can buy for $10, $12 these days. It's actually a quite economic alternative to buying, you know, $200, $300 professional mobile radio terminals. Even if the cheap phones break frequently, it's still going to be an economic advantage. It's also the configuration, this OpenBSC, the NITB configuration, which is what you would use if you want to do security research or something into cellular technology. We extended that over the time with other network elements needed for GPRS, for packet switch communication, because GSM is actually, many people use GSM as a synonymous for any kind of cellular telephony. That's not technically correct. GSM is the system that was originally described in the late 1980s and deployed first around 91, 92, if I remember correctly. And it's only about SMS and circuit switch telephony. There's no packet data in there. So we added these SGSN and GGSN components, which are needed to have a packet switched service, GPRS and Edge. Some people may still remember that these were the first mobile data systems out there in the cellular worlds. Using those components, the last sentence, I'm not so sure anymore. It's pretty stable, and some people are using it actually in production, but still it's less mature than the other components. So this, of course, once you have mobile data, you can, for example, test M2M devices doing that. So if you develop a smart meter or develop some mobile device that includes a modem, then testing against the real network, and if something fails, well, you don't see what's really happening on the network. You don't get a protocol trace on the network. And you don't know, was the network overloaded, was there bad reception, so you don't have a controlled test environment. But by using your own network, basically, you can do that. Mobile malware research, and of course, again, learning actually about the technology involved in all these protocol layers. Because if you think of a GPRS network, and you look at the protocol stack, I think there's like 8 or 9 layers below the IP that you as a user consume. And you know, to me, as somebody who is into networking, if there's some protocol that I don't know about, I want to know about. So I'm interested in how these systems work and how those protocol stacks look like. That's just my personal interest, but there are other people out there who find it interesting to really learn about how these systems work and how they are designed and how they are different from other systems out there. And that's something you can do with this stack. Okay, let's switch to another project which we have in the Osmocom project, which is the Osmocom BB project, where BB is for baseband, sort of not entirely correct, but the naming, you know, it's always the last thing you think about. So what it is actually is an implementation of all the software that you need to run a mobile phone, except the actual hardware transceiver. So we reuse existing phone hardware, specifically some older feature phones that are sold under the Motorola brand and not actually built by Motorola. Using such a phone, basically we remove all the, or we ignore all the original software that's in there, all the binary only firmware that it ships with. But we developed our own software from the drivers, the layer 1, layer 2, layer 3, basically everything that you need to run inside the phone. And using this, you can then, from free software, run a complete phone that you can register to an official network, where you can make calls, do handover, send SMSs, receive SMSs, and so on. Well, okay, I can do that with the phone as it is. Why do I need Osmocom BB? Well, the difference is you can see everything that's going on and you can influence it, of course. So let's say you're somebody who is particularly cautious about not revealing his location. With Osmocom BB, you can put an offset to all the transmissions, so you appear to be further away from the cell, and the network doesn't really know where you are anymore. These are the kind of things you can do once you control the technology, which you cannot do if you just use a black box and a proprietary protocol stack. And of course, you can see everything that's going on. So if you suspect something fancy going on, you have not only the protocol traces, but you can literally look at every part of the software. So yeah, where is this being used? Well, it's mostly actually research and teaching or studying. So applied security research. There's lots of people have been using this over the years. For example, you can fuzz base stations or other parts of the cellular network, because now, for the first time with Osmocom BB, people can send malicious or intentionally malformed messages to any of those protocol stacks on the network side, which hasn't been the case before. So basically, there were a lot of low-hanging fruits in the network implementations where, well, they just didn't think of what happens if a message is not malformed. So we're like in the internet of the mid-1990s, the security mindset sort of. That's what you see in the cellular world. There's an attack called the RATCH denial of service, which is basically an overload of the initial process when you register to a cell, when you establish a channel to a cell. That has been implemented and published about that. So using Osmocom BB, it's easy to do that and to perform denial of service against cells. You can check for all kinds of features which networks recently added to increase or improve their security. So there's some random padding that has been rolled out by a lot of operators to combat some of the A5 encryption breaking, and you can check if a network actually uses that or not. You can also use this to do heuristics on detecting IMSI catchers or other false base stations that might be in the vicinity. So if you're worried about some evil attacker putting false base stations and trying to play man in the middle with GSM, well, then Osmocom BB is a very good technology to look into what's really happening on a protocol level. And once again, well, yeah, you can study and learn how this works. Okay, well, that's basically a lot of GSM-related projects. Let's look at well, actually, yeah, Osmo BTS very quickly about this slide. So far I've been talking about, well, you need this base station, and at this camp in 2009 we used the Siemens base station, so there's still a proprietary element in this chain. With Osmo BTS we also implemented the actual BTS itself in software, so you can now use a combination of different software components, including Osmo BTS and the network in the box and something else that's called Osmo TRX. And run that on a software-defined radio, and then run your entire base station out of software-defined radio. At that point, you don't have any proprietary software involved anymore, and no firmware or anything. That's a closed source at that point. Okay, that was all GSM and related technology. Now there's many other projects in the Osmocom umbrella project that look at different mobile or cellular technologies. One is called Osmocom Tetra, which is an implementation of the PHY and MEC layers of Tetra, which is terrestrial trunked radio, which is used, for example, by police all over Europe for communication. But no, you cannot listen into police with Osmocom Tetra, because they use normally, at least if they deployed it correctly, strong end-to-end encryption. But there are many other networks, let's say at airports or chemical plants or ports, or seaports or something like that, where they run Tetra as a professional mobile radio system, and they don't use any of the security features. So there's no authentication and no encryption involved. So using Osmocom Tetra, for example, in Berlin, in my home city, you can tap into the radio of the subway, so you can basically listen to the subway radio. And there's also a network by Vattenfall, the local electricity utility company, where there's not much traffic going on, but I think they are using or they have this network for disaster cases. So basically, whenever all the other communication channels should break down in case of a bigger disaster, that the utility company can still communicate with people in the field trying to fix the grid or something like that. In Hamburg, there is a network that includes the Hamburg port, and there are several airports in Germany which have completely unencrypted open Tetra communication. And then we think about all the the body scanners and all the security simulation that they do to the passengers, and then on the other hand, all their internal communication is completely public to anyone, and they don't put even encryption or authentication there, which is specified, but they're just too lazy to actually deploy it. So, like on the airport, you can listen to everything that's going on, not between the planes and the airport, where they use regular airband AM, but it's about the staff on the ground, the coordination, which vehicles go where, the buses and so on. That's basically what's communicated there. So using Osmocom Tetra, you can do protocol analysis on Tetra and also decode the voice that's in there. The receiver is fully implemented. Transmitter is only a partial implementation. We never even really bothered to do real transmission. The transmitter implementation basically only served as a test case against the receiver, so we could verify the receiver without having a third-party signal. Yeah, so there is some Wireshark dissectors merged into Wireshark, so you also get a protocol decode like you would get in a TCP/IP network. Yeah, so what to use this for? Well, for analysis, assessment of network security, learning how Tetra works, and so on. Actually, the code has been extended to also, there's also like a cellular data over Tetra, so something like GPRS for Tetra, and that also gets fully decoded, and you actually see some, in those networks that I've looked at, you see IP communication going over this. There's other projects in the Osmocom umbrella. One is called the Osmocom GMR. GMR is, as everyone in here certainly knows, the Geo Mobile Radio, which is one of these acronyms from ETSI, the European Telecommunication Standardization Institute, about satellite radio or satellite telephony. So I was just kidding. I guess nobody here heard about GMR before, but Thuraya, some people might have heard before. It's one of the commercial operators operating a satellite telephony network using the GMR1 standard. And the Osmocom GMR project implements an SDR-based radio modem and PHY and MAC layer for receive. So basically this means you can, using a suitable antenna, which is relatively easy to build, and an SDR and Osmocom GMR, you can get the protocol traces of the decoder. The speech codec by now, sorry if the slide is outdated, is implemented, so it is proprietary, but the reverse engineering on the speech codec has been done, so you can actually tap into calls. There's also some work not done within the Osmocom project on breaking the encryption, and there is a reverse engineered implementation of the, well, encryption in quotes they put on this system, so it's even weaker than the GSM encryption you have on land. Yeah, so well, again, use cases, well, not really anything beyond looking at the security, learning about the technology, and intercepting communication. There's also a project about DECT, the Digital European Cordless Telephony, which has been broken many years before Osmocom even. There was a project called dedected.org, which discovered security issues in the cordless telephony standard. And Osmocom DECT is an implementation of hardware drivers and protocol stacks inside the Linux kernel. So if you compile that and have the right hardware in place, you can actually serve as a PBX and have all the DECT stack in free software. A similar project for OP25, which is APCO25, which is a professional PMR system used in the US, again by police and other public authorities. It can be compared on the same like feature level and so on technology like Tetra in Europe. And there's a project again for an SDR-based receiver and protocol analyzer. So it's pretty much the same, just for yet another communication system. We also did an Osmocom SDR quite some time ago, but then basically RTL SDR happened and nobody was interested in Osmo SDR anymore. And I'm going to get to RTL SDR in the next slide. But it's a small USB SDR hardware that we built with a higher bandwidth that at that time available, the FunCube Dongle Pro, much lower cost than USRP. And yeah, we made it, I think, to like 20 or 50 units, and then yeah, it sort of, the timing was bad because, well, luckily, and I'm very happy about that, RTL SDR happened, which is also the actual source code for RTL SDR is developed in the Osmocom project. And what some of you may have heard or seen this before, even use one. It's basically, there are some cheap DVB-T USB receivers that you can buy at very low cost. And these devices, normally they have a tuner that down converts the signal from the RF into INQ baseband, in analog baseband. And then you have an ADC, which also integrates the DVB decoder, so all the demodulation and so on and so on. But through some special commands, the DVB decoder can be disabled, and you can forward the raw samples into the PC. And then basically it means you can turn one of those consumer grade receivers into a software defined radio that you can use to receive pretty much anything that's within the frequency range and the bandwidth of this device. And the software for actually talking to the hardware and implementing the drivers for it and so on is what we call RTL-SDR in the Osmocom project. There's another project also closer to hardware, which is Osmocom SimTrace, which is hardware and firmware and software for protocol tracing of the interface between SIM card and phone. So if you ever were interested for whatever weird reason in the communication between your SIM card and a phone, or actually any contact-based smart card and its reader, because it's always the same standard that's used. So some people are also using this to look at EMV payment cards using the SimTrace, because it's the same physical interface. So it works, as you can see in the picture. You insert a SIM card adapter with a flex cable into the actual phone. We also have these for the micro and nano SIM cards, not just for the large ones. And the actual SIM card then gets put into the PCB. There's a SIM card reader where the SIM card is inserted, and then there's a microcontroller on the board which sniffs the communication going back and forward between SIM card and the phone. And there's a USB port on the other side, so you basically can get the protocol traces into the PC, where once again they are fed into Wireshark, and we have a Wireshark decoder for the SIM card related protocol. So it's also possible using this hardware to do man-in-the-middle or SIM card emulation. It's just the software is not complete in that part. The software implementation only for card emulation and for tracing has been fully completed. Man-in-the-middle, I think there were some patches at the mailing list at some point, but it's not really integrated. So about SimTrace, there's also going to be a workshop at EMF Camp. If you're interested in playing with this and in tracing SIM card communication, feel free to attend this workshop. I have 10 devices with me, so we can have some fun with those. Maybe one more thing to why would anyone do this? Aside again from, well, I want to understand this protocol and this interface and how it works. Well, there are a lot of things that a SIM card can do to a phone which most people are not aware of. A SIM card can request the GPS position from the phone, for example. Why would a SIM card ever need to know that? A SIM card can send SMSs by itself using the phone, where the user has no idea that those messages are being sent. A SIM card can do all kinds of other things, which is not presented to the regular user of a mobile phone, and that's why doing protocol analysis can be quite interesting to see really what's using this and what's happening in this communication. We also did another small hardware project, and there's many more of these. I'm not going to go through all of them. One is an E1 transceiver, which is, well, if you ever are in need of interfacing with a physical E1 or T1 line, that's a synchronous system which is used a lot in GSM base stations. That's why we implemented it. We built a small board for that. There is protocol stack implementations in Erlang. If anyone here fancies Erlang as a programming language, normally in all the other Osmocom projects we use low-level C, no C++. But here is some projects in Erlang that implement various protocol stacks that are used in cellular networks. I'm not going to go into the details here, but if you're interested in the core network protocols which are spoken on the roaming interfaces between the cellular operators, these are the protocols basically that are used in those interfaces, and we have these implementations. So there's some smaller MVNOs, virtual network operators, that don't have their own radio network, their own physical network, but they only operate a core network. And some of them actually use this code for some of the functional elements they need. There's more Osmocom projects. I'm sure the number 79 is outdated now. I didn't do a recount before today, but there's lots of public Git repositories there, and way more than I can cover in this talk. Often, I mean, in the larger projects or the more frequently used ones, you will find a wiki and some documentation, but some of them there's basically just a Git repository. It's because somebody needed to write some code and put it in there. So it is sometimes RTFS and there is no manual or documentation, but then you can always come to the project mailing lists and discuss questions that you have. Finally, a couple of slides about non-Osmocom projects, which are also related to open source mobile communications. I just want to name them because I think they're also important if you have an interest in mobile communications. There is what's called OpenBTS. Don't mistake it with OsmoBTS that I presented earlier. OsmoBTS is an Osmocom project, OpenBTS is not. OpenBTS is functionally best described as a UM to SIP bridge. UM is the radio interface between your phone and the cell tower, and SIP, well, SIP is voice over IP telephony, so it is a very quick and direct bridge between this radio interface and SIP. So if you don't want to bother with all of these deep protocol stacks and all these strange acronyms and all the complex architecture of GSM, this is a very quick way how to attach a cellular phone to a voice over IP system. There is another project also slightly outdated and unmaintained these days called AirProbe, which is a SDR implementation again for the GSM radio interface, which predates Osmocom and all of the other work that I presented today. But you can use it using SDR hardware like a USRP or something like that. You can use it to demodulate and decode the radio interface of GSM and then feed it again into Wireshark for protocol analysis. It's not so much used these days anymore because you can do the same with Osmocom BB, and Osmocom BB you need a small inexpensive phone and you have an excellent decoder, and when you use AirProbe you need a very expensive SDR and you have a very poor software decoder, so you had to get lots of bit errors and frames just because the quality of the decoder implemented in AirProbe is not as good as the one in the DSP of the phone. So that's why it's a bit abandoned. There is another project called UMTRX, which is an SDR hardware project specifically for the GSM radio interface, which you can use with either OpenBTS or OsmoBTS. It's an open hardware design, so you can also check that out. Finally, one last project that I find very interesting is Xgoldmon, which is basically a software for phones that are based on the Xgold chipset. That's formerly Infineon, now Intel series of GSM baseband processors that's used in some phones. You can see like Samsung Galaxy S3, S2, Galaxy Note 2, and so on. They use this chipset, and there is some undocumented commands by which over USB you can basically enable tracing in the phone, and then you get all the low-level messages from the GSM radio interface, or not just GSM but also 3G radio interface, over USB, feed them into your PC where you run Xgoldmon, which then feeds it into Wireshark again, and you can again look at protocol traces and observe and analyze what the phone is doing in terms of the network. Okay, well, where do we go from here? That's sort of the wrap-up of all the various different projects. Our team member Dieter has been working a lot with 3G, Node Bs from Ericsson and Nokia. The goal is also to run our own RNC with those base stations. We meanwhile also have implemented what's called a home node B gateway. So with certain femtocells, you can now also run your own 3G network, similar to the network in the box for 2G and 2.5G. There's some research into intercepting microwave backhaul links, because a lot of the microwave backhaul links that are between cellular base stations are unencrypted again, and they're only protected by, well, some proprietary encoding. There's research into GPS simulation and some ongoing effort of Osmocom BB with other baseband chips or with SDR, because the phones that we originally developed for are increasingly hard to find these days. Try to find a phone from 2007, you have to go to a museum these days. You can still find them, but it's getting increasingly difficult. There's, well, the femtocell work I already spoke about, and there's some research into proprietary PMR systems, yeah, many other people looking at interesting communication systems out there. And I think it's important that we understand those communication systems and they're not just controlled and understood by very few large corporations on this planet. Yeah, so if you tend to agree that, well, on A, classic internet TCP/IP is boring because it has been researched to death and everyone learns about it at university or even in school. So there are many, many, many other communication systems out there, and never trust the industry in terms of any kinds of claims regarding safety or privacy of those systems. Always have a look yourself, and yeah, I think it's important we can democratize access to those communication systems and to the related projects. So yeah, if you have an interest in any of these areas, please contribute to the project, start your own projects, join the mailing lists, and yeah, let's proceed that way. Okay, that's a thanks slide. I'm not going to read the names, and yeah, we have time for questions. So there's, I can't see, but there's supposed to be somebody with a microphone. Yeah, over there, indeed. So if you want to raise questions, please wait for the microphone and ask the question in the microphone for the recording.
Yeah, I can't see very well, so wave, please. Oh, hello.
Yeah, hey there. Do you have any concern that anything you're doing might get you in any trouble at all?
I don't really have much of a concern in the sense that research into all these topics, there is nothing illegal about it. Of course, if you use it to actually intercept systems, then that is, depending on the national law and where you are and the jurisdiction and so on, might have an issue. But I mean, my standard response is, well, if I manufacture a hammer, it can be used for, you know, nailing nails into the wall, or you can smash somebody's head with a hammer. And it's sort of, just because there are many useful cases of using a hammer, we shouldn't outlaw hammers just because they can also be used to create damage. So it's maybe not a very nice analogy, but that's sort of my attitude to that. I mean, all the tools that I'm talking about, they all exist for the internet, but they didn't or don't exist to that extent for other systems. And I mean, the internet also is alive, and yes, there are criminals online, as there are criminals in the real world, as there are criminals who want to do something fancy in cellular networks. So.
Yeah, hi, very interesting talk. I have two small questions. The first one is, what's the cost of getting a BTS, more or less? If you do know.
It depends. I mean, sometimes, so if you want to get an existing proprietary BTS of from a manufacturer, then you can sometimes on eBay or other online sales, you can find pretty cheap. So I've heard some people, like for 100, 120 euros sometimes. You have to be lucky for that. If you want to go for SDR, well, I think like $500 to $600 you can get an SDR that's capable of doing that. You attach it over USB to a PC and then you run all the software on the PC. If you want to buy a new base station from a manufacturer, then of course it's going to be more expensive. But yeah, so.
Okay, and the other part of the question would be, is it actually legal to run one of the base station?
That depends on where you are and whether you manage to get permission from the regulatory body or not. In many countries, it's possible to get what is often called as non-operational or non-commercial or test or experimental licenses. I don't know how Ofcom in the UK is handling this, but at least it would be worth approaching them about this. So if you say, well, you know, I'm doing some research into cellular communications and so on, and you want to have an experimental license, I'm not sure what would be the response. I know there is a procedure, in every regulatory authority has a procedure for that. Yeah, so unfortunately there is no license-free spectrum that anyone can just use except if you're in the Netherlands. So the Netherlands has a couple of channels in the GSM 1800 spectrum, which is license-free, but that's a peculiarity of the Netherlands. I'm not aware of any other country where this is the case. If you want to play with this technology and not really want to run a network, then what you can do is you can connect the components over coaxial wiring with attenuators. It's not so exciting if you have a wireless phone with a wire coming out of it, but still, if you want to do some research into this, it's a perfectly valid setup, and then you're not broadcasting, you're just feeding the signals over coaxial cable. That's sort of the last resort that you can do.
And so how quickly do you catch up with, because you know, you're talking about trying to reverse engineer and everything, and how quickly do you catch up with things, and how quickly do they come up with new things that you'd have to then, you know, reverse engineer again?
Well, the reverse engineering, we haven't really done so much. It depends on the protocol of the system that you want to look at. I mean, as I said, for this commercial cellular networks, like GSM to LTE, basically, all of them, all the specs are out there. So if you have an SDR and you want to implement something, you don't need to reverse engineer anything. But if you want to work with an existing phone, or if you buy an Ericsson BTS off eBay and want to interface it, then of course Ericsson has modified some bits here and there to make it nice and easy for you to use it. So there's like some additional work required. But in general, it's not so much, I mean, about catching up, I think is not so much related to the proprietary bits in the technology, but it's more related to the pace of the development. I mean, these days, of course, everyone in the industry, I mean, even LTE is old for them. They're talking about LTE Advanced. They're talking about 5G systems where you have 120 megahertz wide channels up to 30 gigahertz or something absurd like that. That's what they are working on. That's what they are looking into. And of course, with every new generation, a new technology and probably a more complex technology gets introduced, and lots of people are required to implement that as free software if needed. But how can I say, with LTE it's slightly different, because there actually is an open source LTE terminal side implementation. So using a USRP or another software defined radio and a reasonably powerful Intel, like a Core i7, Core i5 kind of CPU, you can actually run the entire LTE physical layer and protocol stack in software, in free software on your PC. And you can transmit, I think, about 50 to 70 megabits through that, so it's actually quite useful. That's not something that has happened in the Osmocom project, but still, I mean, there are people doing free software in those technologies, even if they are more advanced than the 20-year-old GSM that we started to look into.
Okay, and the questions we've got. Chap over here, and I'll come over to the back there.
Yes, say if you're, for example, experiencing intermittent issues between two commercial operators, which Osmocom tools can actually help you debug and find out which operator messed up?
Between two operators, so you're talking about roaming situations. Yes. You cannot debug that unless you can tap into the interface between those operators.
But can you at least see that one of the operators actually cooperated, or had less problems than the other, or?
It's difficult. I mean, you can do one of these, tracing on the device. So if you trace, let's say using Xgoldmon or something like that, you can take a protocol trace of what your device is doing towards the network, and you observe that in an operator where it works and in another operator where it doesn't work. Then maybe you can get some conclusions on where the problem might be. But if it's roaming, then I think it's very hard to get any results without actually being able to look at the core network of the operator.
Okay, who's over here?
What's the current state of the art in femtocell hacking?
It's not so... Okay, how can I say? Well, there are some femtocells, I'm not going to name them yet, where there has been made a lot of progress and where we could actually convince the femtocell to talk to our own network and our own network implementation, and there's going to be some news later this year about this. The problem with most femtocells is that by today they have reasonably good security in their in their system. So the idea of a femtocell is that basically you get a small cell into your home, but this cell establishes an IPsec tunnel to the operator that has issued or that has given you that femtocell, and then this cell becomes part of the radio access network of this operator. So you have this for a good coverage in your home. Now, if you want to use it from your own network, well, first of all, you need your own network implementation. We did that with the Osmo IUH and the home node B gateway that we implemented. So from the protocol side, the implementations exist now. But what you still need to do is basically you need to somehow route the cell locally and make it either install your own certificate for the IPsec so it connects to your own IPsec gateway, or disable IPsec altogether so that it just connects over plain TCP to your network implementation. And some people have tried this with Huawei femtocells, UAP 2105 or something like that. And there the main problem was that, well, as there was one specific Russian firmware version where it was very easy to circumvent all the lockdown basically, but all the other firmware versions that you find in the devices that you can find online on eBay or something like that, they are secured, and a serial console and JTAG and that stuff has been disabled. So that's not so interesting. There are some older femtocells which have less security in a sense of physical security. So like the original Vodafone, I'm not sure how they called it here in the UK. I was even, I think, 2009, 2010, sorry? On? No, I think it was called different back then. But anyway, okay, maybe it was called Vodafone On, but they were the first in Europe, I think, to deploy femtocells. And if you look at those, it's very easy to break into them and to route them, but they predate all the standardized femtocell protocols. So basically, you need to speak a different protocol to talk to them. It's a proprietary protocol and not the later standardized IUH protocol. So you basically have modern femtocells that are very hard to break in, which speak a standardized protocol for which there is code, or you have old femtocells where you can break in easily, but which don't speak a protocol that's interoperable and documented. So not so nice, the situation.
All right, I think that might have to be it for questions. Let's get ready for the next speaker. But thank you, Harald. That's very interesting.
Thank you so much.